So as an analogy, if we look at the connection between work and energy, that implies that we looked at the work energy theorem. And when we did that, what we found here is that the work energy theorem essentially tells us this. We wrote it as the network equal to the change in energy here. So in essence, here's what we saw. We saw that if I do net work, then the energy of the system, let me be careful here. I want to make sure I draw this a little bit bigger. So I need to bring this down. That I have this scenario right here, right? That's what the work energy theorem says. So when I look at this thing, look what happens here. If the net work is not equal to 0, then that implies that the energy of 1 and the energy 2 is different. Oh man, I need to move this. I'm going to run out of space. So I got to move this over here. Sorry about me jumping around. But wait a minute. What happens if the two energies are different? That implies a non-equilibrium situation. In other words, if I'm talking about kinetic energy, if I change the kinetic energy, I must be accelerating. I must be either speeding up or slowing down. So in this case, as an analogy, I could say that if I have a positive change in kinetic energy, then I'm speeding up. If I have a negative kinetic energy, then I'm slowing down. That's one way to look at this thing here. But what happens if the net work in this case is 0? Then we say that the energy before and afterwards are the same. So this gives us, in essence, an equilibrium situation. And this leads to conservation of energy. That's what we know about the work energy theorem. Well, what I want to introduce now is the impulse momentum theorem. And the impulse momentum theorem is very similar to the work energy theorem. Okay? And by the way, this defines momentum. This is how you define momentum. Okay? So starting with N2L, I have F net is equal to the derivative of the momentum. So what am I going to do? I'm going to integrate. So if I integrate, what I really got to do is I got to integrate the momentum, and then I isolate the time. And when I do that, look what I'm getting. Is there, I mean, yeah, you could say that an integral can be indefinite, and I'm going to say that's a lie. A true integral is about an area. So what that means here is that I have to integrate between what? Two different points. Check this out. What did I say? You try to tell me momentum of a single point, and I'm going to say that's meaningless. The only thing that's meaningful is differences in momentum. And this is the origin right here. Can you take an integral of a point? Of course, that's craziness if you say that. That's the origin of momentum being meaningful only as differences. And so when I integrate this, I then get an expression that reads like this. I have a change in momentum, and I have the integral of the force as a function of time. And this guy right here is defined as J, and J is known as the impulse. This is the impulse momentum theorem right here. Okay? This is the impulse momentum theorem. Okay? The impulse momentum theorem. I don't like it in this way. Look at the work energy. You didn't see me write it as net work equal to the change in energy. I like writing it this way. So guess what I'm going to do? I'm going to do the exact same thing for the impulse momentum theorem. So my preferred way to think about this is this. P1 plus J equals P2. So look what I'm going to do. Look at the work energy theorem. What am I going to do? I'm going to do the exact same thing. Check her out. Right? I have two possible situations. If this impulse expression is not zero, then it tells us that the two momentums are not the same. So what do we say? We say that this is a non-equilibrium situation. And if it's not equilibrium, then this implies here is that V center of mass is not conserved. That means that V center of mass before and after some type of interaction is not valid. That means there must be an external force acting on the system. It's not appropriate to say external force. We say external impulse acting on the system. So then check this out. If J is equal to 0, then the momentums before and after the interaction within the system is exactly the same. So now we're in the situation of dynamic equilibrium. So dynamic equilibrium tells us that the center of mass is conserved. So what you find here is that when I have dynamic equilibrium, guess what that gives me? Conservation of momentum. And I would call that the second commandment of physics. So now what I want to do here is that I want to go and interpret this thing. Okay, because you got to be a master of this thing. So I want to answer a couple of questions, a series of questions. So what I want to do here is that I now want to interpret the impulse momentum theorem by answering one, what does an impulse do? Okay. Two, what is an impulse? And you'll see that there's more to it than meets the eye. And then the question here, I want to use impulse momentum. Of course, what? bar diagrams. Some of you were probably hoping that I would forget about those things. My response is, hell no. It makes visualization of the problem considerably easier. So let's go answer these 3 questions so that we can then interpret what role the impulse does. Okay, so here we go. So the first thing I want to do here is I want to ask, what does an impulse do? And the reason why I need to answer that question is because most of you will say force, but it's not a force that changes momentum. It's an impulse. So I got to differentiate between these two to make sure it's really clear. So what I'm doing here is that we need to differentiate between a force and an impulse. What's the difference between these two? So if I look at the viewpoint of Newton's second law, and I look at the viewpoint of momentum from the impulse momentum theorem, here's where we go. So the viewpoint from N to L tells me what? Well, it tells me that there's this thing called the net force, which is mass times acceleration. But acceleration claims, what do they claim? Velocity changes, right? It claims a velocity changes. But the question is, it's the F net is the cause of velocity change. But what about from the viewpoint of the impulse momentum theorem? So now I want to look at the viewpoint from the impulse momentum theorem. So what do I know? Well, what I know here is that the impulse, what we find here is that we find that J causes a change in momentum. In other words, the impulse changes, the impulse changes momentum, right? It is not the force that changes momentum. And so when I look at this thing mathematically, I then say that it's this guy, right? Which is quite different than the net force, is the cause of delta P. So they're two different things. And furthermore, the impulse depends on two things. On two things, whereas the net force only depends on one thing, right? The net force only depends on the force, but the impulse depends on the force and time, not one. Well, clearly, if I have a force dependence, which is what most of you are going to think here, all that tells me here is that if I apply a greater force, then that tells me I'm going to have what? I'm going to have a larger change in velocity. But if I have a larger change in velocity, then I must have a larger change in momentum. And that's not unreasonable to think that. But if you limit yourself to that, then you're wrong. Because there's the elusive time dependence. Time is important to momentum. And what I mean by that here is how long of a time force acts tells us about the momentum change. And what do I mean by that? Well, picture-wise, I can draw this as a picture. Okay? So let's think about a car here. Now remember, this is not about distance. This is about time. So you could imagine that I have a car, and let's differentiate these cars by color. Okay, so how about this is our green car. And what we're going to do here is that we're going to apply a force here now. I'm going to apply a force, F, the exact same force. Now, let's go get the red car. Okay, so now here's my red car. I have identical cars here. And so when I think about my red car, I'm going to apply the exact same force, right? Exact same force. But there's a difference. Here, I'm going to apply F over a shorter time. This one, I'm going to do what? I'm going to apply F over a longer time. But wait a minute. The force only changes the velocity. It has nothing to do with time. So then, check it out. This car, in the end, is going to be doing that because I only pushed the car for a shorter period of time. What you're going to see here is that this car then, of course, is now going to be moving with what? A smaller change in momentum, which means a smaller speed. Because I pushed the red car for a longer period, this guy has to have what? It has to have a larger momentum change, which is of course proportional to velocity. But the thing that's different here is that if you were thinking that only the force was important, then the change in velocity should be exactly the same. But the fact that I have different time intervals tells you that it's got to be different. So now that we've talked about the impulse and how the impulse is different than the force, now we should then go and define what the impulse does here.